So over the weekend, I did a race called the Michigan Mountain Mayhem. And one of the things I noticed is that as we're going through the race, my average speed at the beginning of the race fluctuated a lot. And you can see that there's a lot of hills here early on in the race. And in fact, there's hills throughout the race, but my average speed didn't go up and down nearly as much towards the end as it did near the beginning. So a good question is, well, how do you find an average when your function is going up and down like this? Now, average is pretty easy when you're dealing with, just a set of numbers. You add them up and divide by n, where n is the number of pieces of data that you have. But what do you do if you have a continuous value function? How do you find the average there? Well, there's a nice little formula, and no surprise, it's going to involve the integral. So if you want to find the average of some function f of x between two numbers a and b, we're going to first of all calculate this integral. Now, what's that integral going to give me? Well, it would be a geometric interpretation of that integral. Anyone? Yeah, the area underneath the curve, between the curve and the x-axis. So that's good. Now, if you want to turn this into an average, then you're going to multiply that by 1 over b minus a. Basically, this is the equivalent of dividing by n if you had discrete data as opposed to continuous data. And that's going to be your average value. Okay, so let's practice with this a little bit. We'll start with this one. I want to find the average value of the square root of x on the interval 0 to 4. So, okay, let's do that. And I've got a nice little Desmos link here that you can look up as well. So that's this function right here. And I want to start by finding the area underneath that curve between 0 and 4 and above the x-axis. So I'll do that. So example A. That means I'm going to need to integrate the function from 0 to 4 of the square root of x dx, amongst other things. But to get the average value, I got to do more than just integrate it. I got to multiply it by 1 over 4 minus 0. Of course, that's just 1 over 4, but that's going to give me the average. So I'll do that as 1 over 4. Probably want to change this a little bit. Still going to go from 0 to 4, but I'll probably write that as x to the 1/2 dx. Why do we bother doing that? It helps in finding the antiderivative. You're going to add 1 to the exponent, divide by that same exponent. So that's going to give me x to the 3/2 divided by 3/2 between 0 and 4. To continue to clean this up, dividing by a fraction is like multiplying by the reciprocal. So there's going to be 1/4 times 2/3 times x to the 3/2 between 0 and 4. And you can clean that up a little bit if you'd like. It's really going to be 1/6 times x to the 3/2. It's going to be 4 to the 3/2 minus 0 to the 3/2. 4 to the 3/2 is 8, minus 0 is still 8, so I'm going to get 1/6 of 8, and in lowest terms, that's 4/3. So that's your average value. Nice. Let's take a look at it graphically and see if that average value seems or feels like it makes sense. So I'll give you a second to catch up with the writing there. But what we want to do is we want to look at the function and see, well, does 4/3 feel like it's kind of in the middle somehow, some kind of a weighted middle? So we can click on this little line right here, y equals 4/3. And yeah, okay. A lot of the function is below here, but you got some that's pulling it up higher for an average. So yeah. Now what this means is I can look at this and calculate this area in a couple ways. I could calculate the area by integrating like we did, or let me shut this off. I can just calculate the area of this rectangle. So the length times width. So that's going to be 4 times 4/3. That'd be 16/3. That would be the area here. And coincidentally enough, well, actually not really a coincidence, but this area, let's see, that entire area, if you look at it, is also 16/3. So a couple different ways to look at that area. One is just with our calculus, and one goes back to geometry, just length times width. So nice, nice. All right, let's keep going. Let's try another one. Good on the first one? All right, I'm hoping that these are going to be pretty simple. More or less, these are an excuse to give you a nice integration problem. So the next one we're going to look at is going to be the function f of x equals 6x minus 3 sine of 2x between 0 and pi. So let's look at that one. So I'm just going to copy that down. 6 sine of x minus 3 sine of 2x between 0 and pi. All right. Let's crank this down a little bit. Get that in here. And let's come back over to here. If I want to find the average value, then I can do that by setting up the integral. The average is going to equal 1 over pi minus 0 times the integral from 0 to pi of 6 sine x minus 3 sine of 2x dx. And this one becomes a little bit annoying because of one of the things you're going to have to do the integration. Now, as far as the first part is concerned, that's 1 over pi, the integral. Let's split this up. Let's split this up into the integral from 0 to pi of 6 sine of x dx minus 1 over pi again times the integral of 3 sine of 2x dx. Now, why did I do that? Well, 1, because I can, but 2, because the first integral is going to be simple. Second one is a little something on there that's going to be annoying. Nothing terrible, but it is going to be annoying. Let's deal with the first one. What's the antiderivative here? You can take out the 6 if you'd like. 6 over pi times the integral from 0 to pi of sine of x dx. I'm hoping that that one looks familiar. What would that be? Nice, negative cosine. So it's going to be 6 over pi times negative cosine x between 0 and pi minus 3 over pi, taking the 3 out, integral of 0 to pi of sine of 2x dx. This one's more of a pain. Why is it? Why is it more of a pain? Yeah, because of the 2x, all right? It's not in the standard form like we have here, so that we just say, oh, well, let's find an antiderivative. So this one, it kind of depends on you. It's going to require a u-substitution. So let's do a little u-substitution. What should I let u equal?
2x.
2x, yes, well done. So u equals 2x. Du would equal 2. Well, let's see, I'll do du over dx equals 2. And then du equals 2dx. And that's what I wanted because I've got a dx term here that I'm going to need to solve for. So 1/2 du equals dx. That's perfect because now I can do a direct substitution. I've got a dx here and a dx here. So I can get rid of the dx as I do my substitution, change over to u. I should probably also change my units. I don't know about you. I like doing it this way. Some people want to do their integral and then change back. So, you know, that's fine. Let's see. So if I'm going to change my units, I got to calculate two more things. I got to calculate u evaluated at 0 and u evaluated at pi. And see what happens there. Well, 2 times 0 is still 0. 2 times pi is 2 pi. So with all those adjustments, I can now figure out, you know, I can now at least start working on the rest of this. It's going to be 3 over pi times the integral from 0 to 2 pi of the sine of u. And instead of dx, I'm going to write 1/2 du, like that. Let's take that 1/2 out in front. That's going to be 3 over 2 pi. And I think I can do the antiderivative. In fact, someone already gave me the antiderivative here. Antiderivative of sine is negative cosine. So it's going to be 0 to 2 pi of negative cosine of u. Okay, looking good there. Let's bring this one down. 6 over pi, 0 to pi, negative cosine of x. And this is going to be a minus between these two integrals. Going back up to here. All right, let's keep going. That's going to be 6 over pi times cosine, negative cosine. I wish I would have factored out the negative. Let's factor out that negative. I'm going to put it out here and then just deal with a cosine of pi minus a cosine of 0. And I'll do likewise here. Let's factor out that negative. That's going to become a positive, plus 3 over 2 pi times a cosine of 2 pi minus a cosine of 0. Okay, so let's see what happens here. That's going to be negative 6 over pi times negative 1 minus 1 plus 3 over 2 pi times 1 minus 1. Cosine of 2 pi is 1. Cosine of 0 is 1. What happens to this second term here?
It zeroes out.
Yeah, it zeroes out. Nicely said. Zeroes out. That's 0. And over here, I get negative 2 times negative 6. That's going to be positive 12. So positive 12 over pi is your answer. So that's going to be your average. I'm guessing that's a little bit less than 4. Let's take a look and see if it looks reasonable. Let's take a look on the graph. So here's our function. There's your average value. There's your function. Let's take a look at the average value. That looks reasonable. You know, it's someplace in the middle. Should be someplace in the middle. So, you know, without getting overly fancy or technical, at least it passes the smells test. At least it doesn't look absolutely wrong. So let's keep going. Couple more here. Friends. I try and save the notes for you guys. I scan them in and got wet. My water bottle leaked on it. Okay. Let's try example C. So example C asks us to find the average value of this function, y equals 2x e to the negative x squared. And all right. So another chance for us to flex our integrating muscles. C. F of x is 2x e to the negative x squared. All right. And we want to look at this on the interval 0 to 2. I believe that's right. Just double check back here. Yep, 0 to 2. All right, so they're going to have to give you that interval 0 to 2. If I want to find the average value, that's going to be 1 over 2 minus 0, the interval from 0 to 2 of 2x e to the negative x squared dx. Please put in that dx. I do like seeing it. Sometimes I get a little unhappy with it not being there. There's important reasons to keep it there. I'm not going to go through all those now. This 2 and this 2 can cancel. So that gives me the integral from 0 to 2 of x e to the negative x squared dx. Unfortunately for us, there's no product rule in integration. I can't take the integral of x times the integral of e to the negative x squared. In fact, coming up in section 7.7, when we discuss that, one of the problems that you could run into if you're trying to find the integral of this, say, a to 7 or whatever, there's no antiderivative for this function. There just isn't one. So if you're going to try and find the area between this point and this point underneath this curve, how do you do it without an antiderivative? So that's when you start using numerical methods like the trapezoid method and Simpson's rule. But for now, we're in better shape. We can do something here. What would that be? Any suggestions?
U-substitution,
Yeah, u-substitution. So Nicole, what would I let u equal?
negative x squared.
Perfect. Let's let u equal negative x squared. Du by dx is going to be negative 2x dx. Excuse me, just negative 2x. And the next step, we'll get that dx over there. If you multiply both sides by dx, you'll get what I was alluding to, which is du equals negative 2x dx. And that's almost what I want because I've got an x and a dx over here. So let's just get rid of that negative 2 by dividing both sides by negative 2, or better yet, multiplying both sides by negative 1/2. Negative 1/2 du is x dx. And again, that's perfect because that's exactly what I've got up here. Let's change our limits of integration. So let's take care of that as well. So if I consider that as u of x equals negative x squared, I need to calculate u of 0 and u of 2. U of 0, of course, is just going to be 0. What about u of 2?
4.
U of 2 is going to be almost 4. Negative 4, yeah. So you have to square it and then take its opposite. So it's going to be negative of 2 squared, which is negative 4. Nice. Now this gives us a chance to talk a little bit about a little trick or property of integrals that I haven't mentioned before. So let's substitute in all this stuff here and see what we get. Now let me bring this down here. I'm going to reorder this as the integral from 0 to 2 of e to the negative x squared x dx. And with that, I can make a nice u substitution. It's going to be the integral from 0 to negative 4, which looks a little odd for us. 0 to negative 4 of, let's see, e to the u times negative 1/2 du. So just putting in my little substitution, x dx right there gets replaced by negative 1/2 du. Right now.
Well, why do you change like the upper limit of integration?
Actually, technically, I did both. What's unusual about this one, to an extent, is that when you put in 0, it didn't change. So I actually did do both. It's a good question. It just doesn't feel like you did both because 0 mapped back to itself. So now, this might be a little bit unsettling because usually we go from lowest to highest in terms of our limits of integration. And this is highest to lowest. So that looks a little odd. Now, there is a little property of integration that says, all right, we can switch this up. I can go from negative 4 to 0. But when I do that, it changes the sign of my integral. So I get a negative out in front. Now, the interesting thing is that I've got a negative here with that 1/2. So those two are going to cancel each other out. That negative, this negative are going to cancel each other out. I'm going to bring this out here to do that. 1/2, the integral from negative 4 to 0 of e to the u du. All right. At least that looks a little bit better. It doesn't offend our sensibilities so much because it's lowest to highest. What's the antiderivative of e to the u?
E to the u.
E to the u. So it's going to be 1/2. 0, excuse me, not 0. We got rid of that. It's going to be negative 4 to 0 of e to the u, which gives us 1/2 of e to the 0 minus e to the negative 4, or since that's a 1, 1 minus 1 over e to the 4th. Yay. Not so bad, not so bad. Okay, how are we looking on that one? Doing all right there? So a big mistake that people make on these, and it's an easy mistake, it's a small mistake, but it is still a mistake, is people forget to multiply by 1 over the reciprocal of the length of the interval. So 1 over b minus a. And if you did that, your final answer wouldn't have that 1/2 there. So, okay. But in looking at things, if you forgot that 1/2, the average value should look a little bit wrong. Why couldn't this be the average value, this line up here?
Because it's above the entire thing.
Yeah, the average value is kind of somewhere in the middle, right? And you're above everything. Your function doesn't even get up that high, so it couldn't be the average value. I remember hearing a politician once say that he wants everyone to make an above average income. It's like, well, wait a minute, that can't happen. Somebody's got to be below and someone's got to be above for it to be an average. Same thing here. Everything's below here, so it couldn't be the average. If we do take care of that little bit there, shut that off, turn that on, divide everything by 2. Now that looks a little bit more reasonable. All right, so good on us there. All right, one more. So let's keep going, get this done, knock this out. Let's shut these off. So the last one has a little bit of an extra twist in it. We're going to find the average value of the function and then figure out, well, what value of x actually gives me that average value in the function. So the function has to pass its average value at some point, and they're asking you to find that point. So in this case, our function is f of x is x squared minus 4, or x minus 4 squared on the intervals 3 to 6. So this is example D. F of x is x minus 4 squared on 3 to 6. So if I want to find the average value, that's going to be 1 over 6 minus 3 times the integral from 3 to 6 of x minus 4 squared dx. So you've got two choices here. 1/3, 3 to 6 of x minus 4 squared dx. In terms of finding an antiderivative, you can do one of two things here. You can make a u-substitution, which isn't bad, or you could square it out, which isn't bad. Neither of them is that bad, but I want to talk about u-substitutions for just a minute, and then maybe we'll go back to example B, and I'll point out something there. So if I made a u-substitution, I'd probably want to make this so that I could just find the antiderivative real quickly, which would mean u equals x minus 4 du by dx would equal 1. Or in other words, we're in the very special case of du equals dx. And if that happens, it's kind of suggesting that, you know what, you could almost do this without the u substitution. And let's see what that's all about. Now I'm going to change my limits of integration. So u of x is x minus 4. That means u of 3 equals -1. U of 6 would equal 2. And okay, I'm in good shape now. I can change my limits of integration. I finished the substitution here. So it's going to be 1/3 the integral from -1 to 2 of u squared du. Okay. So it's going to be 1/3, and then u to the 3rd over 3 between the limits of -1 and 2. So 1/3 and 1/3, that gives me a 1/9. I'm going to pull that out in front. And then I have a u cubed here. Okay. So let's keep going. That's 1/9 times 2 cubed is 8 minus -1 cubed is going to be -1. So 1/9 of 8 plus 1 gives me 1. So if we look at the graph, then here's our graph. Let me zoom out a little bit so we can see it. There we go. The average value is 1, which looks a little strange. You're like, okay, well, that's the average value. But somehow or another, that means that the area to the left and the area to the right, they kind of balance out so that the average value is 1. And in fact, this Desmos graph here actually helps us answer the last part of the question. So let me get rid of those two. And that is find the values for which f of x equals its average. So there's actually two. One of them is at x equal 3, and the other one is at x equal 5. Both of those places, the function is going to have a value of 1, which is its average value. Now, If you're asked to solve for that and you needed to, basically what you're gonna do is set x minus 4 squared equal 1 and then solve. Personally, I would just take the square root on both sides. Be careful that on the right-hand side, there's plus or minus a square root. And if you're careful to solve, you get two answers, 5 and 3. So we're good on that part of the calculation. Let me go back here and talk a little bit more about stuff that's going to help you moving forward. Right here, we ended up with du equals dx. So it means I don't really have to adjust much at all, right? If I'm making my u substitution, I don't have to worry about a constant or anything like that. It's kind of saying that you can do what you think you would do with this. That is, find the antiderivative by adding 1 to the exponent, divide by the same exponent, and you're done. It would have worked out the same way because our du equals dx here. Also, in that same spirit, looking back here, we did a lot of work to do our u substitution. But if you could just find an antiderivative by thinking about it, then maybe you can avoid having to do a u substitution. Now with this one, it was just kind of a quick, oh, all right, well, u equals 2x. Let's do a little thought experiment. What's the derivative of 2x? Yeah, it's just 2, right? Now, if you were differentiating this, you'd have to apply the chain rule, you'd end up multiplying by 2. But integration is the opposite of that. So what would be the opposite of multiplying by 2?
Dividing.
Divided by 2. So if you can keep that in mind, it's going to save you a lot of work. You're going to be able to look at something like this, integral of sine of 2x dx, and say, okay, well, I know the antiderivative of sine is cosine or negative cosine. So it's going to be negative cosine of 2x. And then instead of multiplying by 2, I've got to divide by 2. And bam, there's your antiderivative. So it's a lot more user-friendly than having to go through all that u substitution stuff. If you can get that u substitution, or if you can do that stuff in your head. Now, it's not that important for this class. But boy, in Calc 2, man, you're not going to want to get bogged down doing a u substitution on all these little problems. You're just not. So just a little word to the wise there for you on that one. Any other comments or thoughts here? All right. Let's call it a day on this section, and I'll see if I can't get this posted someplace.